So last time we saw a new concept that is called BIBO stability. This concept, in simple words, means that we have our system and we have an input u of t that is bounded by a quantity, capital U. Then in that case we have that the output is bounded by another quantity that we call y. So long as we inject something that behaves well into the system, and by behaves well we mean that it doesn't diverge, then also the output is not going to diverge. And this notion was specified starting from an initial condition x0 that was assumed to be equal to 0. So this was the concept of BIBO stability in simple terms. Then we specialized this notion to a first-order linear system to see under what conditions the first-order linear system actually is BIBO stable. So we said that for a first-order linear system that was following these equations, x dot equal to ax plus bu and y equal to cx plus du, we found that the system output satisfies the following inequality. We went through some mathematical steps, inequality, and we found that y of t can be upper bounded by the following: the absolute value of c times b divided by minus a times 1 minus the exponential of at plus the u of t. And in this case is if a is different from 0. We are dividing by minus a, so we have to somehow assume that a is not 0. In the case when a is equal to 0, then the upper bound that we found, so if a is equal to 0, the upper bound can be found in this way. Either we make a go to 0, otherwise we repeat all the same steps, replacing a with its value 0, and we find in either way, both ways are legitimate. We find that this is given by, oh, I forgot a capital U here, CB capital U times t plus d u of t. These were the two possible upper bounds. One holds when a is different from 0, and the other holds when a is equal to 0. And we found that this quantity here, this quantity is bounded if a is less than 0. Okay? If a is greater than 0, this quantity is not bounded. The question that I posed is, what about, so if definitely if a is less than 0, we have proven BIBO stability. So first observation is, if a is less than 0, we have proven, and of course I'm assuming implicitly and c times b is not 0. So if a is less than 0 and is bound if a less than 0 or c times b in modulus is equal to 0. So if a is less than 0 or c times b is equal to 0, the bound guarantees stability. Now the question is, if a is greater or equal than 0 and c times b is not 0, do we have BIBO instability? This is the question I left you with last time. The answer is yes, and we are going to prove it in a very simple way. The answer is yes. We can prove it using the step response. Let me explain why. If by contradiction the system was BIBO stable, then the output should be bounded. The output should be bounded for the step response as well, because the step input is going to be is a bounded input, so the output has to be bounded too. So if for a greater or equal than 0 and CB equal to 0, we the system where BIBO stable, the output y of t should be bounded when the input u of t is a step. However, for the step response for the step input u of t, that looks like this. It's going to be something that is equal to 0 and then becomes u bar. The output y of t has the form, and we have computed it because this is precisely the step response. Y of t equal to c exponential of atx0 can be neglected, and we can just rely on the response that we have computed before, that is given by c times b c times b times u divided by minus a 1 minus exponential of at. This is for a different from 0, and for a equal to 0, this is equal to cb capital U times t. Okay, so let me repeat this once again. The question is, if we have a greater or equal than 0 and c and b that are both different from 0, do we have BIBO stability and BIBO instability? So is the system actually unstable? The answer is yes, it is unstable. We can prove it using the step response. Okay, but this was not proven from this because we were just finding some upper bounds that were diverging. To find out if the system is BIBO unstable, it's not enough to find an upper bound and then to say that the upper bound diverges, because this quantity y of t, the absolute value y of t, could actually be bounded. You upper bound with something that diverges, and so you cannot conclude BIBO instability. To conclude BIBO instability, we need to be a little more nuanced, and we use the step response. So we assume that we have a greater or equal than 0 and c times b different from 0. If in this case the system were BIBO stable, the output y of t should be bounded because the input is if you consider the step input is bounded. But y of t, when the input is a step of this form, has this expression. And observe that these quantities are not bounded for c be different from 0 and a greater or equal than 0. So if we put, if you inject a step as an input to your system and you have that c times b is different from 0 and a is greater or equal than 0, then you obtain a y of t that is unbounded, so definitely the system is BIBO unstable. Okay, so this answers the question that we asked last time.